Dr. Karnik with New Age Science Academy, and in today's session, we are going to be looking into how to calculate pH for acids and bases. So first, let's start with how to calculate pH for a strong acid and for a weak acid. So let's go to this question. So this question is, calculate pH of the following solutions. The first solution is 0.1 molar HCl solution, and the second one is 0.1 molar HCN solution. The Ka value for this solution is also given to us. So let's start with the first one, HCl solution. When we are looking into this solution, we know that we are looking into a strong acid. And calculating pH for strong acid is pretty simple and straightforward. We all know that to calculate pH for any acid, pH is equal to negative log of hydronium ion concentrations given by that particular acid. And a quick review of what are hydronium ions. Whenever you're working with any kind of acid, like a generic acid like HA in this case, it combines with water molecule to form hydronium ions and its conjugate base. And how are these hydronium ions formed? Well, this HA is going to dissociate into hydrogen ions and its conjugate base. This is what we put down here. These hydrogen ions are going to combine with the water molecule to form hydronium ions. These are the hydronium ions we talk about when we are looking into calculating the pH. So let's go back to calculating pH using this particular formula. So in this case, when I'm looking into a HCl solution, HCl is combining with water to give you hydronium ions and Cl minus ions. To calculate pH, we are going to look into this concentration given by the HCl solution. Now, as we know, since this is a strong acid, it is going to completely dissociate. This is also shown by this single arrow pointing in one direction, which means that every molecule of HCl is going to dissociate into hydronium ions. So for example, if I gave you 5 molar HCl solution, you are going to end up with 5 molar hydronium ions because every molecule of this HCl is going to dissociate into hydronium ions. So in this case, since I have 0.1 molar HCl solution, I know this is going to give me 0.1 molar hydronium ions. Since I know how many hydronium ions I have, I'm going to put it into the formula to calculate pH. This is going to be equal to negative log of 0.1. And that gives me a pH value of, when you do the calculations, the pH value is going to be 1 in this case. This is how you calculate pH for a strong acid. Now let's look into how to calculate pH for a weak acid. And this is where we go to our second solution, which is a HCN solution. So as you know, HCN is a weak acid, and therefore, when you have a weak acid, you are working with partial dissociation. So in this case, this is a weak acid. We have partial dissociation, and therefore we get a Ka value, which is the dissociation value at equilibrium. So let's first put down the equation for this weak acid. HCN combines with water molecule, and here, since it is partially dissociating, I'm going to be using a reversible arrow, and it is going to give me hydronium ions plus its conjugate base, which is Cn minus ions. Now, I have to find out this hydronium ion concentration at equilibrium. Remember, since it is not completely dissociating, I cannot use this value directly. Because it is a weak acid, I have to find the hydronium ion concentration at equilibrium. And of course, to find the hydronium ion concentration at equilibrium, I'm going to be using the ICE tables, which stands for the initial concentration, the change that needs to change in the concentration while it is going towards equilibrium, and the concentration at equilibrium. So let's look into the initial concentration of HCN. I know the initial concentration is 0.1 molar, so I'm going to put 0.1 here. Now, since this is a liquid phase, I don't take this into account. All of these are aqueous, so we do care about the concentrations. In this case, for everything that is an aqueous phase. And in this case, initially, I have 0 of the hydronium ions and 0 of the CN minus ions. This is the first initial step, and I just have the acid. Nothing has started dissociating. Now, as we start marching towards equilibrium, there is going to be a change. And the change is going to be such that the concentrations of the reactants are going to go down, and the concentration of the products are going to start going up as the reactants are getting converted into products. Therefore, the HCN, which is a reactant, its concentration is going to go down. I can just put in it as negative X, minus X, going down. Here, the hydronium ion concentration and the CN minus concentration are going to go up since products are being formed. Therefore, I'm going to put it as plus X and plus X in this case. Now, at equilibrium, I'm going to get the concentration 0.1 minus X. Here I'm going to get plus X and plus X. Now, since I have the values at equilibrium and I also have the Ka value, I'll be using the formula Ka is equal to the concentration of the products divided by the concentration of the reactants at equilibrium. So in this case, oops. In this case, I'm going to be looking into the concentration of hydronium ions multiplied by the concentration of CN minus divided by the HCN concentration. And remember, this is all at equilibrium because the Ka value is calculated at equilibrium. So let's put in the equilibrium values here that I'm having. So this is X times X divided by 0.1 minus X, which is also equal to X squared divided by 0.1 minus X. Now, in this case, there is a way to simplify this particular equation. First of all, let's look into the Ka value. We know that the Ka value is very small. And you know, Ka value is telling you about the dissociation rate. It's telling you about how much dissociation is happening in this HCN because it is basically the product concentration divided by the reactant concentration. If this Ka value is low, it is telling us that there is not much dissociation happening till it reaches equilibrium, right? Therefore, the value is very small. And if the dissociation happening is very less, it's also telling us that this change that we are talking about is very small. A very small change has happened and it has reached equilibrium. Therefore, the amount of products are very less compared to the reactants. Hence, the negative 4.9 times 10 to the power negative 10, which is telling you very small dissociation. All right. So since this X value, this change is very small, it could be 10 to the power negative 4, 5, 6. But since it is so small, 0.1 minus this small number is not going to be significant. Therefore, I can conveniently get rid of this negative X, and I can say that this is equal to X squared divided by 0.1. Now I'm going to just substitute the values Ka for Ka, and this value is 4.9 times 10 to the negative 10 is equal to x squared divided by 0.1. And then when I calculate for x, my x value comes to 7 times 10 to the negative 6. So now I know this x value, which is the hydronium ion concentration at equilibrium, is 7 times 10 to the negative 6. Therefore, the pH calculation is pH is equal to negative log of hydronium ion concentration at equilibrium. This is equal to negative log of 7 times 10 to the negative 6. And when I calculate for the pH, my pH value comes to 5.2. These are the steps involved in calculating pH for any weak acid. In our next video, let's look into how to calculate pH for a strong base and a weak base.